Hello and welcome to episode 5 in the series on GPU programming. In this episode, we are going to discuss some performance characteristics and main factors that influence the performance of the GPU. We'll also introduce the roofline model for assessing our code's performance with regards to the hardware possibilities. When we run our code, there are three main areas in play. The first one is obviously our GPU, and it's directly connected to its high bandwidth memory, so our GPU's VRAM. And there is also the CPU that can schedule kernels on our GPU, as well as copy data to our HBM. As you might expect, performance can be a problem in all three of those. The time that we spend running the code on the CPU is called an overhead. The time that we spend loading data from memory is our memory access latency. And finally, the time on the GPU is our actual compute time. Let's first look into our overhead. In our case, it is the time that we spend loading the dataset from disk. And it currently takes around 2 seconds to do that, while our 10 epochs of training take around 9.5 seconds in total. The first obvious thing that we can do is to optimize our CPU code. I managed to get it down to 1 second by using some more optimized string parsing functions. But we want to mitigate our overhead even further, and one thing that you can notice is that we don't need the full dataset at the start of the first epoch. We only need the data that we will be working on. So we can execute the CPU and GPU code in parallel, where the GPU already starts training our network on the first batch, as the CPU loads the next one in the background. Now, this does not eliminate our overhead. We still need to load all of our data during the first epoch. So if we optimize our epoch time, our first epoch will still be limited by the time that it takes to load the data. So we didn't actually eliminate the overhead. We just blended it into our GPU code to hide it. And the limiting factor is not going to be exactly equal to our data loading time, since the CPU also schedules GPU kernels and copies data into memory. Right now our training code looks somewhat like this, and I've omitted some parts for better readability. We load the full dataset before stepping into the training loop. Then in each epoch, we go through our dataset by batches. We run our forward pass, copy the results to the CPU, check our accuracy. We then run our backward pass and update our weights and biases. And we don't actually need to do much to get our dataset to load in parallel. By design, CUDA does not run synchronously, so when we run our kernel, the CPU will not wait for the kernel to finish, and calling other kernels will add it to the queue, which the driver will manage for us. And when we call some synchronous function, so in our case CUDA memcopy, it will wait for the kernels to finish executing. The first thing to do is to schedule all of our kernels before running our synchronous call. That way, we can keep the GPU busy while loading our batch. And now we can just create a function that loads one batch at a time and place it just before our synchronization point. Let's now get into the real juice, which is evaluating and improving the performance of the code that runs on the GPU. And as I've mentioned in the beginning, we can have two kinds of performance issues with our GPU: time spent doing the compute and time spent accessing memory. Our compute time is bound directly by the throughput of the data type that we are using on our GPU. For example, a 4090 has 82.58 teraflops throughput for 32-bit floating point numbers. And flops is just how many floating point operations we can do in a second. Our memory is bound by bandwidth, which for a 4090 is 1.01 terabytes per second. As you can see, we can load our data from memory much slower than we can actually do the computation. This introduces another very important metric for our kernels, which is how many floating point operations we are doing per each byte of memory access. And our computational intensity metric brings us straight into the roofline model, which is a great way of visualizing our performance bottlenecks. We can put our maximal throughput and bandwidth on a graph to visualize what's the maximum performance that we can get based on our computational intensity. If we are on the right side of the graph, that means that we are compute bound. The GPU is working at full power and not waiting for anything. And that is usually the place where we want to be. Although there are some things that we can do to improve performance in this situation. And to name a few examples, we can change our data type to a more performant one that allows more flops. We can try to improve our algorithms to require less computation. Or we can use more specialized hardware, such as tensor cores that allow higher throughput. Finally, we can make NVIDIA shareholders happy and just buy more GPUs, if they aren't sold out yet. And if we are on the left side of this graph, we are in a bad spot. Our GPU is bored and is not doing any work because it's waiting for the data to arrive from memory. The good news is that there are a lot of things we can do to get ourselves out of this situation. We can use different kinds of memory, but that will be the topic for the next video. Or we can do something called kernel fusion. To show an example of kernel fusion, let's look at our biggest bottleneck, which is ReLU. We are doing two memory accesses, one read and one write, both of size 4 bytes, so that's 8 bytes of memory access. And we are only doing two operations, one comparison and one assignment. This gives us just a quarter of floating point operations per 1 byte of memory. So what we can do is to take our forward pass kernel and fuse them together, completely eliminating the two memory accesses that ReLU introduced. And if we look at our backward pass, we have the exact same situation. So there is nothing holding us back from fusing those kernels too. With those changes, we managed to get from our initial timings of 2 seconds of data loading and 0.95 seconds per epoch, totaling in 11.5 seconds for full training, to a first epoch taking 1.1 seconds of work and data loading, and the rest taking 400 milliseconds, giving us a total training time of around 5 seconds, reducing it by more than a half. But wait, there's more. Since our data and network is very small, it's currently highly underutilized, because the kernels are not even filling all of the possible threads. This is a bit like cheating, but if we increase our batch size from 16 to 64, we can parallelize our calculations even further and get to just 120 milliseconds per epoch, leaving us with a final improvement of 5x over the original code. With this, it's time to end the episode. Using no magic at all, just simple kernel fusion and parallelization, we managed to improve our performance significantly. And this was just a toy example, operating on very small data. In the next episodes, we are going to look more in depth into memory organization of CUDA and how to leverage it to get maximum performance. Subscribe if you don't want to miss it. Also, leave your feedback in the comments, like the video and share it with your friends. As always, I link the code in the description so that you can play around with it on your own. I bet that you could squeeze out even more performance out of it. And if you do, share your changes in the comments. Thank you for your support and see you in the next episode. Bye!